Okay, let's start. So I prepared some notes for the more engineering aspect of R1CS. This one is pretty easy to understand. Okay, so reference is a rare skills zk book and Circom tutorial, also the Circom doc. Okay, nothing special. Let me go from here. So for the next 4 weeks, I'm going to cover graph 16 from end to end. So we're going to start from a single problem statement and build Python code to implement the algorithm. Okay, so this week we are going to talk about R1CS. Next week is a QAP, and third week is a alpha, beta, gamma, delta thing. Okay, so in the last week, I think I'm gonna implement some high technology into this, so make improvement to my own code. So this week is pretty easy. Yeah, it's just R1CS. Let's go from this problem. So in my implementation, I chose this problem saying given a four vertices in a graph, your job is to prove the graph is bipartite. And of course, in a zero knowledge way. Okay, so a prover needs to handle 4 colors here. So either the color is 1 or the color is 2, because bipartite means we want to separate all the vertices into two groups, and it is equivalent to 2 coloring problem. Okay, so for the vertices in group 1, we want to color it with 1. In the second group, we color it with 2. So in a witness, the form will be like 1 2 1 2 here. So this is a problem. So the terminology I'm using is from Circom. So the witness means public input plus private input. In Circom, the first entry is always 1 because it needs to handle the constant term. So this spot is always reserved to be 1, and this is always public. So in our case, we don't need any like sometimes you see out here, but for this problem, we don't have output. So the only public input is 1, this constant term, and we have 4 colors. They are either 1 or 2. So we are just like artificially set up the rule, because you can also say like 0 1 here, it doesn't matter, or you can say 3 5, it doesn't matter. So the to make this simple, we just say like 2 coloring, 1 color is 1, the other is 2, and you need to give me 4 colors to prove that 4 vertices are from 2 groups, so that the graph is bipartite. Cool. So this one is called public input. This R1 to X1 to X4 are called the private inputs. So the terminology is a little bit different as in the book, but this is what Circom uses. Cool. So yeah, verifier has access to public input, which is this constant term 1. Prover has access to everything, because this public input you can, like, everybody can see, right? So prover actually generates this private input because he's proving the thing. So he has access to all the private inputs, of course, and also the public one. Okay. So the verifier can see the first one, and the prover can see the entire thing. Yeah, and also you can define like intermediate signals in Circom, but in this case we don't need it because the problem is pretty easy. So the first job we are going to do here is turning this problem into arithmetic circuit. So this requires some cleverness, you know, like we are proving the vertices are bipartite. So what does it mean is we are providing 4 colors, right? So the first condition is they are either 1 or 2. The second condition is different vertices from different groups. They must have different colors because the definition of bipartite. So how to represent that in arithmetic circuit? Pretty easy. If we want to check a value is 1 or 2, you just say, okay, so x1 minus 1 times x1 minus 2 equals 0. Do the same for all the 4 inputs, the four private inputs here, okay? So set constraints on them, and you just simplify the equation a bit. But actually in Circom, you don't have to simplify this. You can just say this because each constraint is quadratic, and you can tell, even in this form, you can tell the equation is at most quadratic, okay? So you can just write this in Circom. But to make it easier in Python, I simplify this systems of equations, right? So into this form. That's the R1CS form for condition 1. So for condition 2, we want to say different vertices from different groups. They have different colors, right? So x1, x2, one of them is 1, the other is 2. So the result is always 2 because we don't have other options here. Say, for example, in 3 coloring problem, you have color 1, 2, 3. Then you have to write down a table here. Like write down a table and pick out the value that satisfy what you want to do here, right? But in this case, it's pretty easy because we only have 2 colors. So the only possibility is 1, 2, or 2, 1. So yeah, we create these constraints. That's for the second condition. And this is already in R1CS form. You just have to move to the other side. So yeah, that's the arithmetic circuit. This, you turn it into R1CS. Pretty simple for this problem because we don't have to flatten anything. But for example, you have like a cubic equation here, say times x1 minus 3 here. Then you have to manually flatten the equations, right? So that will make the process more complicated, but this is pretty easy to do here because the problem I chose is very simple, okay? So we have a system of equations of 7 equations here. The next step is to turn them into a matrix. So why matrix? Because after that step, so after like everything, we are going to do QAP, which is the Lagrange interpolation stuff we talked about last week, right? So we first turn R1CS into a matrix, and then we extract every column vectors and then squeeze them into a polynomial. So that's why we want to turn system equations into matrix form, because that would be easier to do the Lagrange interpolation stuff later. So yeah. Yes.
Sorry, I just wanted to mention, since I have to run in a bit, I wanted to mention
Yes.
for your example, it's a really nice example, and I think it's fairly cool, like in the next chapter, when you guys read that, to go back to this example and check if like everything is actually constrained that you wanted to constrain. Because like I think there might be some things that you still might need to like constrain for this, but I think it's a very nice example to revisit after. So just to mention before I run off.
You mean like constraint like which part? I'm a little lost.
Oh, I just mentioned, for example, constraint that there only exist 2 colors, and that you are in an environment where an attacker could not provide you, for example, like you didn't talk about it now, but if you're in a binary, if you're in a bit setting, you would have 0 and 1s, right? That's you would need to constrain that, because otherwise an attacker would, for example, give you like another color, and which would then result in thinking, like depends on the modular arithmetic you're in, if you don't talk about it here, that the 2 would become a 1 in that setting, or things like that.
Like even I provide constraints here, the attacker can do something else.
Yeah, I think you don't, like, since you have like 1 or 2, like I need to like think about an example, but I think you can give you an example where I can give you a different inputs. You didn't constrain the type of the input. You didn't say what x1, x2, x3, and x4 are supposed to be. They could be like, if they're in F, like if they're just byte arrays, it can be a lot of things, or integers or something. So you would need to do you need to make exactly sure that they can only be these 2 values. You know what I mean? You know what I'm trying to say?
I understand what you mean, but from my knowledge right now, I think the constraints here are okay. Like unless you provide like a POC to me.
Okay, yeah, I can.
Because I don't know, like how do you attack this?
Okay,
no, because I constrain the thing to be either 1 or 2 in the field, in the scalar field, right? So I'm doing this in, for example, like Circom. I'm constraining all the X to be like field element modulo P. Like how do you provide something else? Because in Circom you can only provide the field elements, right?
Okay, so I think that information, for example, is missing from this description. I just wanted to highlight it because, like in the next,
yeah, I understand what you mean. Like,
it's like
something
very
like a range check, right?
Exactly, and like it's very intricate to design actually problems and circuits for it. So that's why I wanted to mention it, and design constraints. And I think it's a good example to think about all the like attacks that are possible. So
yes, that makes sense.
So I'm going to head off. Sorry for interrupting. I just wanted to mention that for the next session.
Oh, sure.
Okay, thank you. Bye-bye. Sure.
Yeah, bye-bye. See you next week.
See.
Okay, I'm gonna take a look at that later. Okay. So here maybe you need to check something like overflow as well, I think. Because you can provide like P plus 1 if P is the scalar field modulus. So it's the curve order. Okay. Yeah, probably something like that. I don't know, but yeah, like in so in my code right now, I only have these 2 conditions.
For the second condition, can you explain why the last statement that you've written, it's implied by 1
this
and
2? Yeah, I forgot to mention it. Yeah, because you see like x1, x2, you only have 2 options, right? So for example, like x1 is 1, x2 is 2. So 1, 2 here, and then you have 2, 1 here. Or otherwise, this is 2, 1, 1, 2. So that's the only possibilities, right? So this constraint, I think, is pretty clear if you write down the truth table. This is implied by 1 combined with 2. So you are saving 1 constraint here, but like for such simple problem, you can actually just write down here, like, and then build a circuit from here. It doesn't really matter because right now we have 7. If you add this, you have 8. Yeah.
Okay. Yeah, I think I need to write it down.
In practice, I think you can just do a little bit more to be safe, right? If you you got a complex problem, it's hard to figure out. Yeah. But here, yeah, I'm just trying to be smart and skip this. Because the truth table tells you only two possibilities.
Okay, thank you.
Okay. Let's continue. So we have some concerns here, but we're gonna accept that 7 constraints here are good for now. Let's move on. Yeah, actually it doesn't matter if you add more constraints, like the process is still the same. The only difference is you have a bigger circuit. Yeah. So when you turn the systems of equations into matrix form, I think this is pretty obvious if you have taken linear algebra class, because in textbook they usually tell you like matrix is for converting system equations into matrix form, right? They tell you that in chapter 1 probably. So how do you do that? Let's look for an example. So let's keep in mind that the witness vector A is like the standard that tells me how to transform this matrix, right? So the final form we want is L times A. This dot is matrix multiplication. Okay, this dot. And the circle is the Helmholtz product. What does it mean? It is element-wise multiplication. So for example, if you have two matrices, A1, B1, C1, D1, A2, B2, C2, D2, then you do element-wise multiplication. The first term is A1, A2, second is B1, B2. You got what I mean, okay? So it's not like a standard matrix multiplication. It's kind of similar to dot product, but it's between two matrices. Okay, this is called the Helmholtz product. The final form is this, but if you don't see it, don't worry. We're gonna walk through an example right now. Yeah, just one more comment that the number of rows equals to the number of constraints. In our case is 7, so we have a matrix. Now we have 3 matrices of row 7 and column 5, because the number of column is the dimension of the witness. Okay, so 7 rows and 5 columns, like a rectangle matrices. Okay. So let's do an example for the first row of each matrices. Okay. So for example here, we write down this witness as a column vector first, right? And for example, we take the constraint 1 from here. So it's this one, right? We copy here. This constraint, we can see it is quadratic. Therefore, we can break down into x1 times x1 equals 3x1 minus 2. That is saying, okay, we are breaking this equation into 3 parts. So the first part is 1 row of L. So the left one, right? Left L, right R, and this is capital O is the result. Okay, so this is the O part here, R and L. So after we separating this, we can transfer it into a matrix form, right? So for example, this R1, you can find it in the witness. So R1 is the second entry, okay? So you mark this second entry in the row as 1. Since there is no other stuff here, you can just mark 0 everywhere. Okay, so the first row of L is 0, 1, 0, 0, 0, because 1 represents x1, which is here. So for example, in the future rows, if you see oh, x2 is here, then you just mark this entry 1. Cool. So do the same for R. They are the same expression, therefore the representation is the same. So 0, 1, 0, 0, 0. Okay, so in the first row of O, you actually see why we added this constant term 1 in witness, because we need to handle constant part. The constant part here is the -2. You can just write down -2 here, right? Yeah, like imagine you did not include this in the witness, then we would be having a hard time here to handle this constant term, right? So x1, 3x1, therefore in the second entry here is 3. Okay, so this is the thing. Second entry 3, a constant term -2, and then you just do the same for all the constraints. Therefore, you will have 7 rows here, 7 rows and 5 columns. That's how you transform system equation into this matrix form, right? So why is a Hadamard product here? Yeah, you can just go backward and do this computation. I just did this computation for the first row. Okay, so it should be pretty clear that it is Hadamard product instead of normal matrix multiplication here. Right. Yeah, this is kind of ugly because I only did 1 row, but actually you have to compute all the 7 rows and do computation here and verify is good. Okay. Questions so far? I think it's pretty easy. It's like the first lecture of linear algebra class. This it should be pretty easy. Okay. Okay, no question. Good. So in the end, we will have this a 7-row and 5-column matrix times A. We call that A is the weakness. Weakness usually we write as W, but in the paper I think it is A in the graph 16 paper. Okay, so I'm using A here. And L times A, Hadamard product, R times A equals O times. Okay.
Just a quick question: are these matrices public or okay? But A is hidden, or A is what the
public. I think matrices are public. Oh wait.
Okay.
Yes, matrices are public. But A is a public.
Got it. Okay.
So right now, like for today, just forget about zero knowledge. Okay. So up until R1CS, we don't have zero knowledge. The zero knowledge part comes in when we multiply everything with the G1, G2 point we talked about last time. That's the quote unquote encryption part.
I see.
Yeah, that's the zero knowledgeness. R1CS, I think it has more universal use like outside of zk space. I think this construction comes from some other part of cryptography, like this is pretty universal. Like you transfer things into a circuit and then into matrix. Yeah. A is private here, but why we can do this computation? Because right now we are prover. Okay, so everything we are doing right now, we are doing it as a prover. Therefore, prover has this secret A. But later, when prover generates that proof, he needs to encrypt that A, like that information somehow into elliptic curves. Okay, so in the end, the proof that prover generates is 3 points on the curves, but 2 of them are G1 point and 1 of them is a G2 point, I believe. Okay, in graph 16. So right now there is no zero knowledge part, and also there is no snark. There is nothing. You see, like the succinct part, we will be talking about that next time in QAP. Like right now, it's not even succinct because you can see the matrix is full of zero. You can, like abstractly, you can think of this information is pretty loose, you know, like I want to something succinct, but imagine I have like 1,000 constraints here, then I will have 1,000 rows, and most of the entries are zero, so this is not very effective. How to make it succinct, we're gonna talk about that next time, is a Lagrange interpolation. Okay, so we talked about that last week, but next week I'm gonna show the code and also an example. Okay? Yeah, that's all the theory. After that is engineering. Okay, so I'm gonna show you how to implement this RNCS in Python. These are all the libraries we are going to use. Okay, so to represent matrix, we use np.array. So NumPy array is a pretty standard way to do matrix, and then Galois is for doing modular arithmetics over the finite field FP. So the nice thing is this library can turn matrices into that field form and also polynomial. So we can do everything as a GF. Yeah, we're gonna call it Galois field. So GF something. Okay. Don't worry about this. This is some Python magic map reduce stuff. Okay. So and also import the elliptic curve things here. Yeah, we are not going to use them today. It's for next time. Okay. This is for the encryption part, quote unquote. So it's not really encryption, but you get what I mean. Okay. So we are hiding the thing, so it becomes zero knowledge. First, we initialize a Galois field with this curve order. So I need to make a note here that in the entire algorithm, we work with the scalar field. So this curve order represents the scalar field. I think we talked about that before. Okay, so base field is field modulus. We are not going to worry about that. Curve order is a scalar field because we are going to convert everything into G1, G2 point with a scalar multiplication in EC. Okay, so we are going to work with this field, but as a debugging trick, you can define a smaller curve order and debug everything and then go back to the original thing, because this one is gonna take like 3 minutes to compile, I think. Yeah, on my Ubuntu. So for debugging, you can just specify something smaller. Okay, so let's go through this Galois library. Yeah, here I demonstrate how it's used. You can initialize a GF. This is a Galois field. So initialize a field through this constructor, and then you can wrap normal integers into this field elements like this. Okay, so if you are not familiar with this Python repo, this means the return value of the last computation. Like this underscore represents this GF3 stuff. Okay, so so you can wrap integer into a field elements, and also you can convert it back into integers. Okay, addition, multiplication. Also, you can do subtraction, also division. But remember, this division is not integer division. This is a division in a finite field, which means you multiply the multiplicative inverse of the thing. Okay, this is the division in finite field. This is very different. Okay, so in normal Python, you can do this. So this power function, you can compute the multiplicative inverse and specify the field modulus. Yeah, they are just equivalent. Okay. Yeah, I said this just now. It can handle matrices and polynomials pretty easily. So you can declare a NumPy matrix as NumPy array like this, and then wrap it with the GF. GF is the field we just declare. Okay, wrap it and do operations on the GF matrix. You can do the same for polynomials. Specified field here. Okay, so this is the these are the coefficients for x. Like you can just read from right to left, right? This is constant, and then the coefficient for x squared, coefficient for x cubed, and so on. Okay, so this representation in array is equivalent to the polynomial representation. Equivalent. Okay, so how to implement this in Python? Pretty easy. Like we just computed this by hand, right? We computed this LR and O matrices. This is pretty easy to understand. I think the nuance here is you have to consider negative numbers because you don't have that in a finite field. So for the -2 constant term, you have to wrap it with curve order -2 because this curve order is a modulus. It's a modulus of the scalar field, right? So you just like plus -2 plus field modulus. Oh man, this is so hard to express because curve order is actually a modulus of the scalar field, but field modulus is also a constant in the library. Field modulus is a thing, but we never use it. Field modulus is for the base field. Okay.
Wait, so if you had just written GF and then in
yes.
Brackets you put -2, that would not be the same thing?
No, because because I don't think it works because if you put GF here, then NumPy doesn't recognize Galois library.
I see.
You know what I mean, right? Because NumPy is like a more universal thing. It doesn't consider like a small name like this. I think Galois is a small name library, right? So this Galois has like consider NumPy, but not the other way around. I think so.
I see. Okay.
Yeah.
Interesting.
So the only thing left here is computing the witness. Yes, because right now we are the prover. Okay, so we can generate this witness. These are the secret values. Okay. And so in practice, you shouldn't do this in a public script, of course. Okay. But for simplicity, like just imagine we are the provers and we know the answer. The answer is pretty easy, just 1 2 1 2. Okay, so this is so red, green, and red, green. This is a two coloring solution to the problem statement. Okay, and the witness can be represented as NumPy array as well. Okay, so constant term, public input. These are the private input. Okay. Yes. Okay. And then we can do an assertion to test if the matrices and the witness are correctly generated. Yeah, just do the L times A Hadamard product. The thing, yeah, Yeah, so this assertion is just the formula here. This one. Okay. Good. This is pretty easy to understand. We talk about a lot about public inputs, private input. I'm gonna skip this part. Okay, this is pretty easy to understand. So the only public input in our case is the one. Okay. all the x1 to x4, they are private. So you can do a Python slice like this, okay? So this is like slice up until the index before L plus 1, so up to 0. So this is like equivalent to A0. This slice index, if on the left, it means starting from L plus 1. So everything after the index 0. So from index 1 to the end. Okay. That's the Python part. We can also do R1CS in Circom. Pretty fun. This one is pretty fun. So in Circom, how do we implement the problem we just talked about? Yeah, just like this, pretty intuitive. So a convention in Circom is you feed in the inputs. If there are more than one input, then you do this like array form, okay? So also you can say, okay, I gonna set the length of the array of the input as a parameter n, and in the main function, main component here, you can specify like how long you want the input to be, okay? So this is 4. So this is 4, and the input is of length 4. So this is the witness, okay? So this is a secret input. We feed into here. A convention is we do that in an array. So instead of saying A, B, C, D, right? That's pretty annoying. So we're gonna say input as an array, and then condition 1, condition 2, and put down the 7 constraints here. Yeah, this is pretty easy to understand. Like, yeah, you just translate R1 to R4 like 1 to 1, right? Transfer into like in 0, in 1 stuff. Yeah, this is pretty easy. Super easy, okay? R1CS. Yeah, Circom is just a wrapper of R1CS together with some functionalities to make your life easier. Yeah, slightly easier, not very easy, okay? Basically, you are writing R1CS in Circom. Yeah, this is a pretty low-level language. So a pretty important thing to mention, I think I just mentioned it. In Circom, every element is a field element. So they are not normal integers. For example, like all the in 0, in 1 here, they are not integers. Okay. They are field element in ZMOP PZ. ZMOP PZ, you should know by now, is equivalent to finite field FP. Okay, so in a field of this number, yeah, just remember, like everything ends in 617. This is PYECC, the BN128, the curve order. Okay, yeah, you can check that. So, just in my personal experience, I never use this field modulus somehow. I think it's because this information is embedded into elliptic curve addition and scalar multiplication. I think so. Okay, so you will never touch this constant. So everything, for example, if you want to implement this this algorithm, everything you work should be like associated to curve order, I think. Okay, so yeah, I never use field modulus. Yeah, so just remember, like anything ends in 617. This is a curve order. Curve order is the modulus of a scalar field, and this is the modulus of the base field. They are different. Okay, so they are similar because of a theorem. I forgot the name, man. Something like has is bound, something like that, you know, like saying field modulus and curve order should be similar but not the same. Yeah, something like that. Don't quite remember, I can look up. And yeah, Yeah, that's how easy it is to write this problem in Circom. But yeah, it's pretty high level, so we're gonna dig deeper into the compilation and see what's happening behind. Okay, so behind the scene, how it works. First, we compile this using the compilers. Okay, everything went okay. Yeah. So we know our code is correct. Okay, so generate RNCS file. So remember, we were using a wrapper of RNCS. We were not really like writing RNCS. So we need to generate that. How do that using this command? Okay, so dash RNCS also export the symbol file. This is to we generate the symbols. So in the future, we can provide input in input.json as symbols. So this is like the same idea in binary files, like if you ever done reverse engineering, you want to save a symbol file to make your life easier. Otherwise, you just like this compiler gonna generate all the nonsense name to you. Okay, so this is the symbol file, and check out this RNCS. You can see use this SNARKs to print the RNCS file, but the content is pretty stupid. This is not readable. Why? Because this is -2. So recall this number is very close to field modulus. 583. 581. Oh man, this. I'm a little confused actually. Why 161? Oh man. Wow, I found something. I'm gonna put a question mark here. I'm a little confused. I'm gonna tell you later, okay? I'm gonna tell you guys in Discord, but I'm a little confused on this part, I think. I think this should be -2, right? No, this should be -1, and this should be -2. Why is this 161, this 151? Does anybody know? But whatever. So the idea is this large number is curve order minus something. Okay. So in our constraint, I think this is like p-1. This is p-2, but somehow it's giving me this. Oh, I know why. Hold on. Oh, I know. Okay. This is curve order. See, curve order is 617. This one is 6161. This is 6151. So I think this is a bug, Could be Circom bug. So Circom is appending this one somehow, like a placeholder or something. You see this one everywhere, but it's actually not a number. Okay. Yeah, it's printing this one somehow. I don't understand. But this is, yeah.
Sorry, what is this equation showing us, or what is it representing?
Okay. So this is RNCS.
Okay.
So for example, just look at this line starting with this info. Okay. Mm-hmm. So this is the first constraint. The first constraint is here. So recall what was the first constraint is x1 minus 1 times x1 minus 2 equals 0, right? So x1 is just the input 0. Cool.
And then there's plus main.in 0. So this.
Yeah, this plus so this one is a -1, but you cannot do that in a finite field.
Sure.
Therefore, you have to be around. So this large number equals to -1 plus curve order.
Okay.
So So this makes sense because curve order ends in 617. This is 616, but somehow Circom is printing this one somehow. So this is redundant. This is like a bug or something.
Okay.
Yeah, I just make a comment here. Printing one at the end of each huge number. Yeah, I hope people reading this now can figure out. Yeah, this was pretty confusing. So whatever, this is a p minus 1, this is a p minus 2. Okay, so a Circom thing. Yeah, I got confused, but whatever. Okay. Yeah, I think the rest are pretty easy to see. Yeah, you see, it's printing one everywhere. So this term should be 2. It's printing 21 somehow. Yeah, it's kind of stupid. Okay. And we finished that part. Okay, so we gonna compute the witness, but first we have to generate this WebAssembly file somehow. I don't know why, but I have to do this part. So it generates a directory called the project name _JS. So you go into that directory. You're gonna say okay, I'm gonna create a new file called input.js. No, input.json. So what is this? This is R1 to R4. These are the private inputs. So in input.json, this is not witness. Okay, so this is just user's input, which means the private input. In our case, private input is x1, x2, x3, x4. Okay, so there's no constant one term in the front. Okay, so this is input, private input. You're gonna create a file called input.json and copy paste this into the file as input. Then we can compute the witness. So you are using these commands. Okay, so in the end, the witness is 1, 1, 2, 1, 2. So this first term is the constant term we just talked about. Okay, that's all for today. Any questions so far? Yeah, I think it's pretty easy to understand. Okay, so compared with the book, right? My approach would be very easy to understand. I think this is just like high school level. Okay, so the only confusing part we got stuck here, I figure out. So this Circom is printing this one somehow at the end of every number somehow. Pretty stupid. Okay, we figure out everything. Okay? Pretty easy.
Did you use Circom for the Grad 16, like the entire implementation?
No, I use Circom for my rare skills bootcamp homework.
I see.
So Grad 16 was pure Python. So I wrote like 300 lines of Python, including comments. So it's a pretty small, pretty small program, but you have to figure out the math because although today we didn't do any math, we're gonna do that next week. Next week is pretty heavy, and the week after is even heavier.
Okay.
So math is gonna come, but it's not like a high level math. It's like a polynomial inner product manipulation. It's pretty annoying. Okay, and why I did Circom? I just want to introduce this because the behind the scene part is pretty interesting. Also, this is not everything because next week we can see under the hood, Circom generates the powers of tau. No, I mean SNARK.js is generating the powers of tau stuff and like how to prove things in practice. We can demonstrate that next week. Okay.
Awesome. And are you done with the rare skills bootcamp? Was it?
I finished the zk bootcamp.
Nice.
I finished
Would
the
you
zk
recommend
bootcamp a
it?
week ago. I do. I actually, I do recommend it because I can tell you that it's pretty hard to do it on your own. So although the bootcamp doesn't provide any secret knowledge, I think you will have a higher probability to finish the entire thing and have your Graph 16 implemented at the end.
I see.
But yeah, but why I say with high probability? Because I think only like 3 people, like we have like 11 people at the end, and then from the beginning, okay? So in the end, I think only 3 people show up. So you have like 30% of chance if you join the bootcamp. But if you didn't join the bootcamp, you know, like how many people talk about ZK last year, you know, on Twitter.
Right.
Like I see hundreds of people talking about it, but they still didn't learn anything, you know.
Right.
So yeah, join the bootcamp, but you have to study on your own. Yeah.
And just one more question regarding that. Did you get did you opt for the one-on-one mentoring sessions as well?
Oh, I didn't because
didn't?
I'm actually mentoring other people.
Oh wow. Wow, because yeah, I mean that's just an additional cost. I
Yeah.
wasn't sure whether to.
Yeah, I know, but I don't know if Jeffrey will be happy with this or not. I don't think it's worthy to do one-on-one because you have to do your own work. I mean,
Right.
unless you are super rich and super busy, like you are senior or you are CTO or something, probably you want that, right?
Okay.
I mean, the course is pretty well structured. You can do it on your own. Like, I spend probably like 5 hours per week.
Okay. Wow, that's
Yeah,
not that much.
Yeah, I mean, ZK is not very hard if you learn it the easy way, right?
Yeah, I think it's just a very steep learning curve in the beginning, but once you get through most of the overwhelming mathematics, I think it becomes easier.
I don't see why people think it's hard, at least. I think for me, ZK is okay. It's like average-ish difficulty. I think it's fine. Yeah.
Thank you for your feedback. Appreciate it.
Okay. Thank you for attending. Yeah, I hope Jeffrey won't block me after this. Okay. So that's everything for today. Next week we're gonna go over QAP, Lagrange interpolation, Schwartz Zippo lemma. Yeah. Next week is all about polynomials. Okay.
Oh, all right. Thank you for your time.
Okay. Thank you. I will see you guys next week.
Bye bye.